Energy levels. In the year 1913, Niels Bohr proposed an atomic structure model describing an atom as a small, positively charged nucleus surrounded by electrons that travels in circular orbits around the positively charged nucleus. So, just like planets around the sun in our solar system, that is how he described it, with attraction provided by electrostatic forces, popularly known as Bohr's atomic model. Well, it's basically an improved version of Ernest Rutherford or Rutherford's atomic model, overcoming its limitations. Rutherford's atomic model failed to explain the stability of electrons in a circular path. Rutherford stated that electrons revolve around the nucleus in a circular path, but particles in motion would undergo acceleration and cause energy radiation. Eventually, electrons should lose energy and fall into the nucleus. Sorry for the drawing, but that's the idea. This electron here will crash into the nucleus. That's Rutherford's theory in his atomic model. But Bohr sees something wrong with Rutherford's atomic model theory. As the result, Bohr modified the Rutherford model by requiring that the electrons move in orbits of fixed size and energy. He also said that energy of an electron depends on the size of the orbit and is lower for smaller orbits. So the radiation can occur only when the electron jumps from one orbit to another. Again, even though Bohr modified the Rutherford model of the atom, Bohr's atomic structure model was not completely correct. But it has many features that are approximately correct, and it is sufficient enough for much of our discussion for today's lesson. Because the Bohr model is the easiest to explain a certain thing. That's the main thing. Once the basic ideas are understood, students can then progress to the quantum mechanical model. The quantum mechanical model is the more correct and accurate than any other model, such as this one. So these are the electrons orbiting around the nucleus. Now the electrons with a negative charge are going to be attracted to the positive charge of the nucleus. And the circles that you see here, circles, orbits, or shell, or energy levels whatsoever, we can use interchangeably. These terminologies are represented as K, L, M, and N, or N equal 1, N equal 2, N equal 3, and N equal 4 are the shell numbers indicated by the letter N. So remember, K shell isn't equal to 1. That is the energy level that is closest to the nucleus, has the value of 1, N1, then N2, N3, N4. And these are called energy levels. Energy level from the textbook is called principal quantum numbers of shells. As I mentioned earlier, orbits or shell, electron shells, or even circles are terminologies that we can use if we are referring to as energy levels. So don't confuse the terms. Energy levels are fixed distances from the nucleus of an atom where electrons may be found. So why it is called an energy level? Because Bohr also hypothesized that if an electron absorbed just the right amount of energy, it would jump to the next higher energy level, but not to the nucleus, of course. Then, if it lost the same amount of energy, it would jump back to its original energy level. However, an electron could never exist between two energy levels. You have to remember that. For example, imagine you are climbing a staircase. Energy levels are a little like the steps of a staircase. you can stand on one step or another, but not in between the steps, right? So the same goes for electrons. They can occupy one energy level or another, but not the space between energy levels. So that is how it works. Energy level can only hold a certain number of electrons. The first energy level here on this diagram is K shell, can only hold 2 electrons. The second can only hold 8 electrons, that's the L shell. The third can only hold 18 electrons for the M shell. And the outermost is the fourth energy level, the N shell, can hold only 32 electrons. So here is the formula we can use to predict the number of electrons that can fit into a shell. A formula is 2n squared. For example, the maximum number of electrons that can fit into the fourth energy level is 2n raised to the power of 2. Now, you have to write 2, and inside of the parentheses, you have to place the number there, what particular energy level. In this case is fourth energy level. I have to write 4 inside of that parenthesis, raised to the power of 2. That gives me 16. So 2 times 16 equals 32 electrons. Also keep in mind that the further the electron goes away from the nucleus, the more energy it takes. This electron here in the M shell has a higher energy since it requires more effort to pull the electron a greater distance from the nucleus. So it requires more energy as it further away from the nucleus. Another good example of energy levels in the real world is the fireworks. If electrons jump from a higher to a lower energy level, they give off energy, often in the form of light. This explains the fireworks pictured on the screen over here. When the fireworks explode, electrons gain energy and jump to higher energy levels. And when they jump back to their original energy levels, they release the energy as light. So that's why the reason why when you see the fireworks display in the sky, you see different colors. Why? Because different atoms have different arrangements of electrons. They give off light of different colors. And that's it for today's lesson on energy levels.